And then we also saw one example. So let me, can you see my screen?
Yes,
Yes,
sir.
sir.
Okay.
Yes.
So then we also saw one example of an orthogonal projection. It was, let me recall this because I'll need this example again in today's lecture. So I gave you one example. So what was that? So if suppose we have an inner product space V, and if suppose U is a subspace of V, which is of finite dimensional, it's a finite dimensional subspace of V. So V can be anything, but U is a finite dimensional subspace of V. Now, if we fix a basis, since U is a finite dimension subspace of an inner product space, so U itself is an inner product space, so finite dimension, so it will have an orthogonal basis or orthonormal basis. So let us take just fix an orthonormal basis of U. So let's say this is an orthonormal basis of U, and then based on this, we can define a linear transformation from V to V. So how do we define this? So I'm using this notation P subscript U. So that means it is a projection on U. From V to V, it is defined by this rule that if I take any vector in V, then it goes to this one. You take an inner product of this V with this Qi and I equal to 1 to m. So that means you consider this linear combination of these basis vectors where the coordinates are given by this. Now you can see that this element here in this element belongs to U. In fact, you can show that this is a linear transformation such that Pu square equal to Pu. That means it's a projection. Not only that, the range space of this is U, and the null space of this is U orthogonal complement. So that means this Pu is a orthogonal projection. This is what we saw in the last lecture. So this Pu uh, is a projection. That means ortho is a projection. Not only that, it's an orthogonal projection because range of this is U and null of Pu is U orthogonal complement. Okay. So this is what we saw in the last lecture. Today I'll start today's lecture with one use of this orthogonal projection, or you can say one application of direct application of this orthogonal projection. It is called like approximating a vector from vectors from a subspace, or it is also known as best approximation, or you can also consider it as a as a minimization problem. So let me just write this first and then we'll discuss. I'll just give you some idea and you can complete this complete the details. So let me write this. It is also known as best approximation.
सर आई सर 1 to n होना चाहिए.
I equal to 1 to n. Yes, you are right. This is 1 to n. Or you can consider this as solving minimization problem. So what it is, let me write this first. So suppose that we are given a vector v. I'm just defining this problem. Suppose we are given a vector v in an let's say inner product space, and suppose that U is a subspace of V. Okay, it's a subspace. Then a best approximation to V by vectors in U is a vector U belongs to U such that, so in the language it might look like very like confusing, but when I explain it will be very clear. such that the length of this vector v minus u is less than equal to length of v minus w for all w belongs to u. So what I'm doing here, so I'm starting with a vector v here, and I'm also given a subspace u. So what I need to do here, I need to find a vector in the subspace u which is nearest to this vector v. So that means I'm finding a vector v which is closest to a vector in the subspace u. So I'm finding that vector u here. So that vector u I'm calling as a best approximation. So that means it is a best approximation of this vector v by vectors in u. So a best approximation to v by vectors in u is a vector u such that the length of v minus u is less than equal to length of v minus w for all w in u. That means this is the vector. You can consider this as a distance between v and u. So the difference of this vector v minus u, and if you take the length, you can consider this as a distance of v from u. So you can say that the distance of v from u is smallest or is less than equal to distance of v from any other vector, is less than equal to distance of v from any other vector in u. Okay, so this vector u is the closest vector to v uh, by vectors from vectors in u. Okay, so for example, you can understand this as an example in R2. For example, if I so look at this problem in R2. So suppose that we are in R2, that means here, and if so, how to solve this problem? You can get an idea from here. So suppose that we are in R2, and let us consider that so R2 with a standard inner product, and let us consider this as a subspace. Okay, x-axis as a subspace. So this is our u. So x-axis, sorry. So this is our u. Okay, this is our u. All right. Now, if I take any vector, let's say any vector in R2, let's say V. Okay. Now, can you tell me which vector in U would be closest to this vector V?
Perpendicular diagonal.
So yeah, so you just draw a perpendicular from this vector V on U, and wherever this perpendicular meets the subspace U, uh, that vector would be vector nearest to this V from U. Okay. So what I'm saying is that you just draw a perpendicular here, and then wherever this perpendicular meets that vector, that means this vector here, this one, this vector is the vector which is nearest to V from vectors in U. Okay, let us call this vector as U. This is your, okay, and what would be this perpendicular? This perpendicular is actually V minus U. Right? This vector here, if you look at this vector is V minus U. So we are given this vector V. What we did, we just draw a perpendicular, and wherever this meets, this would be. Now, what is this U? Can you find out this U? What would be this U? Can you tell me explicitly what would be this U? Depending on this vector V. So if you look at this orthogonal projection, so this is what we did, right? We just projected this V on U orthogonally, right? We just drew a perpendicular on U, and then based on that we decided this vector U. This is the idea, and it's also very clear from this picture. So what is this? This U is basically the orthogonal projection of V on the subspace U. This is what we did. So basically this vector U is this one, VU. So now you know how to find this PUV. You know what? How to find this orthogonal projection? If you look at this example, what you need? You just need, so you have a vector space V here, which is R2 for this example. Now this U is x-axis, so this is also you just need a basis for U. That basis you can take as E1, orthonormal basis of U. E1 you can take, and then you can compute this PUV, right? So what it would be? This PUV would be just you just write this as V Q1, which is just E1 I'm taking, and E1. So if you compute this is your PUV. So now you know everything V was given. Even you know what orthonormal basis for U, because U is also given. So you can compute this. So you can tell what would be this factor U. So this way you can find closest vector or nearest vector to V from vectors in U. But then here this is R2, but in general also this idea works. I mean, at least we can guess that, okay, if, because we can, for any vector space V and a subspace U, if U is finite dimension, then we can compute this projection of V on this U, and we can claim that vector which we are obtaining by projecting this V on U orthogonally, that vector would be the nearest vector to V in vectors from U, right? So that is what is our guess, and then we will, in fact, one can prove easily that this vector, this which you obtain by projecting V orthogonally on U, this vector is the vector which is nearest to U, nearest to V. Okay, is it okay, the idea? So here you can prove this also. Let me write this as a result. So suppose that we have a inner product space. So in general also we can prove this. Whatever I just explained in this example, we can prove this. Suppose that we have an inner product space, and suppose that U is a subspace, finite dimensional subspace of V. And suppose we are given a vector V in V. Then then the best approximation to V by vectors in U is given by this vector P U V. That means by projecting V orthogonally on U. That means, in other words, what you can say is that this vector, so the distance of V minus this vector PU of V is less than equal to the distance of V minus W for all W in U. All right. So this one can prove. So how to prove this? This is very straightforward. The proof is very straightforward here. So let me write the proof here. It's one line proof. So if I just show, I can compute this PUV, right? This projection is known to me. Once I know V, I know the subspace U, then I can compute this PUV by using an orthonormal basis of U, as we did in that example, right? So this we can compute. So I will just show that if I take any vector W, then the distance of V minus W is always greater than equal to distance of this vector. Okay. Now you look at this. Let W be any vector in U. Okay. Now if you look at this one, V minus W square, the same thing I can write as V minus, I will add this vector PUV to this, and I'll subtract the same vector in this. All right. Now you can see here, you can see here, I can take this as one vector and this is another vector. Now, what is this vector v minus puv, pu of v? It is this vector here. If you look at in this example, it is this vector. So this vector is actually orthogonal to u. So this, if I take the difference of p and the orthogonal projection of v on u, that means this v minus pu of v. This is a vector which is orthogonal to u. That means it is orthogonal to every vector in u. So this vector v minus puv, this is orthogonal to u, orthogonal to subspace u. And here this vector, where is this vector? So
On the same
what
line.
is this vector? Where is this vector? Not line. So
On
here we are
you.
talking about subspace. In u.
Subspace, sir.
In U.
Yeah, in u. So this is in u, and this is a vector which is orthogonal to u. So what I can write from this? If you just expand the use the inner product property and the fact that this vector is orthogonal to this, then what would be this
Norm v minus
quantity?
PUV squared
Yeah, so
plus
it would,
PUV minus.
yeah. So this would be norm of v or length of v minus pu of v square. Please keep
Hmm.
yourself muted.
Hmm.
Please keep yourself muted. If you're not asking anything, then please keep yourself muted. Now, this thing here, this is always less than equal to, or sorry, greater than equal to, because both these quantities are, you can see here, both these quantities, these are non-negative quantities because length is always non-negative quantity. So this is always greater than equal to length of v minus pu of v square, right? And you are done. This is what you were trying to show, that the distance of v and pu of v is always less than equal to distance of v and any vector w in u. So this vector p of v, which you get by projecting v orthogonally on u, is the closest vector to v. This is easy to compute once we know the vector space, once we know the subspace u and the given vector. Using that, we can easily find which vector in u is nearest to v. Okay. And now clearly, if v, so v, I have taken here v in the vector space v, but if v belong to u, so it can be in u also. Then this, what would be the nearest vector to this vector v? So if suppose this vector which I am starting with that belongs to u itself, and now if I looking the nearest vector in u to this vector v, what would be that vector in u?
सर
So
v
U
हो
ही होगा.
जाएगा.
v itself
v
ही हो
होगा.
गया क्योंकि the distance is 0. Yeah. So now you can use this idea or you can use this result in solving this thing. So the exercise is following. I'll give you the idea, but you can complete the exercise. So the exercise is that find a polynomial. You just have to use this best approximation to this. So now this is, you can see the application of this, and it is of practical purpose. So find a polynomial p in, let's say, of degree 5, let's say, that approximates sin x, okay, on this interval minus pi to pi, as well as possible. So now what you have to do here, you have to find a polynomial p of degree less than equal to 5 that approximates this sin x on this interval as well as possible. Now, if you want to use this idea, so basically what you are trying to do, you are trying to find a best approximation of this sin x, this function sin x, uh, from the vector, from the polynomials of degree less than equal to 5. Okay? We are looking for a best approximation of a polynomial of degree less than equal to 5 to this sin x. All right. Now, if you want to use the best approximation, so then what you need to first fix an inner product space V, okay, with respect to some inner product. Then you can consider for this vector space a subspace, which you sort of here, if you realize in this exercise, this subspace should be this one. Sorry, this one here. And then you are given this vector V. V is sin x. And then you can just use whatever we have used so far. Now, can you give me some idea what should I take here? I can you guess something? What should be my vector space first? You tell me that this I can fix this vector space with respect to this inner product, and then I can consider this P5R this as a subspace of that, and so
The
Vector
space
space
of
of
all continuous,
polynomial.
it's a continuous function
continuous function on what?
on
So take
minus
inner
pi to
product fx comma gx equal to 0 to 1 ft gt bar dt integration में.
Yeah. So what we need here, we let us. So this was our
Then
problem.
we
Okay.
find
Yes. Yes. So I
then we
understand
find
what you're
one
saying.
Li vector 1x x square x cube and x4.
Then
Then find orthonormal basis from here from Gram-Schmidt process.
yeah, exactly. That is the
Then
idea.
we find orthogonal projection. Then distance approximation.
Yeah. Yes. So now you know how to do this. So this was the problem. So first you mathematically formulate this. Okay. So this is how it works. See, this was our problem. You first write the mathematical formulation, whatever things you require clearly. So then once the problem is clear, the solution you can immediately find. So for example, let me write this. So mathematical formulation of this problem, you can do it. So I'm just writing this separately just for your understanding that this is how it works. You first mathematically understand that this is the problem. Once you formulate it mathematically, things would be very clear. So for example, here, if depending on this problem, you can choose, as you are suggesting, you can choose V as a space of continuous function from minus pi to this interval minus pi to pi to R. So this is a vector space you can take as over R. And this, there is an inner product also, as you are suggesting. There is an inner product on this V, which is defined by this integration. So minus pi to pi ft gt dt. So this is all. This is an inner product. So V becomes an inner product space with this inner product. So now we have our inner product space. Clearly, these polynomials are continuous functions. So if you restrict them on this interval, there would be this P would be. So this U you can take as P5 uh, over R, right? So it's a polynomial, but you have to restrict them from minus pi to pi. Okay? So this U is the polynomial space of polynomial functions on this. Okay? You can take this as minus pi to, or you can just yeah, as a subspace if you want to write, then you can consider this as. So these are polynomial functions of degree less than equal to 5. Now you can take your vector V as sin x. Now see, we have everything. This U V is the infinite dimension inner product space, but U is of finite dimension. Its dimension is 6, and we have a vector V. And now what we are trying to do, we are trying to find best approximation of this vector V uh, in U. Okay, by vectors in U. So this is mathematically now we have understood, and we now also know if I write again this problem differently. So what is my problem now? So this was given, and my problem is to find the best approximation. That means I want to minimize the distance of V minus U. Let me write this with a square from vectors in U. Okay.
Recharge खत्म
So
हो गया।
so I know what it is. It is actually, let me again write. What is this? The solution would be, so here V is sine x. So again, let me write this in terms of the vectors given here. So I have to minimize U in U. My subspace is P5. It's a space of polynomial functions on this interval. So you restrict your polynomials functions on R to this interval, and then this quantity here, what it is, you can just write it in terms of the inner product given here. So basically, it is minus pi to pi ft gt. So here ft gt both are same because v minus u, length of v minus u square is just inner product of v minus u with itself. So it would be sine x minus u square dx. Okay, so this is my problem. And since this is just the best approximation problem, I also know what would be the solution. So the solution of this problem would be from previous result. So from previous result, you can easily write that the minimum of this so the best approximation of sine x by vectors in U by polynomials of degree less than equal to 5 would be this one. That means you just project this sine x orthogonally on U. So what would be this? So it's a projection of sine x on this subspace U. So this would be the answer to this. This would be the solution. Now you just need to find out what is this. As one of you suggested that you can do this once you know an orthonormal basis of the subspace U, because then you can easily compute this. But what would be an orthonormal basis for this? So there is a way. You don't know at this point, you cannot quickly give me an orthonormal basis for this, but you know how to find an orthonormal basis. So you just first find a basis for this. So it would be 1 x square, x cube, x4 to x5. So that means these form a basis, and then you apply Gram-Smith process on this basis, then you can make it orthonormal. Okay, you can generate an orthonormal basis. Once you know orthonormal basis, then you can easily compute this one. Okay, and that would be your solution. So this you can finish, this you can complete. I just want to mention that um, this gives this orthonormal this best approximation. This gives us another way, or you can say it's a linear algebra way or linear algebraic way to approximate like a given function. And this also improves, for example, for this particular example, you can check that this also improves upon what we have learned in calculus. So in calculus, like we have a way to approximate sin x, right? The sin x, you can use the Taylor series expansion, and you can approximate sin x on this interval minus pi to y. So for example, what I'm saying is the following, that if you so you are given this sin x, and then you can use Taylor series expansion up to degree less than equal to 5. So it would be x minus x cube 3 factorial plus x5 5 factorial, this something like that. Okay, so this is one approximation, and then we have another approximation which is given by this best approximation. So this is from calculus we know, and this what we have learned now from linear algebra, right? So if you compare both this, so this is easy to, sin x is given to you, so you just draw minus up to from minus pi to pi, you draw this sin x. Okay, so what would be this? It would be something like this. Okay, minus pi to pi. And then you draw this tx from minus pi to pi. Okay, this whatever approximation you have got, you will realize that when you do this, you will get some approximation. When you draw this tx here from minus pi to pi, you will see that it would be something like this. It will approximate this function in something like this. So up to this, this would approximate, and then in the neighborhood of pi and minus pi, it won't give a good approximation. But then you, if you draw this px also, because this would also be a polynomial. So when you draw this one here, the approximation which you have got from linear algebra, this will be sort of exact approximation on this interval. It would be something like this. And you then you can convince yourself that whatever way we have learned here, that gives us another way to approximate sin x, and it improves upon what we have learned in calculus. Okay, so anyway, so this is just, you can observe. So as I mentioned, we are still left with one topic in inner product. This is like linear functional and adjoint. So adjoint one can define. So for example, if you have a matrix A, so I'm starting a new topic, and it's just a new concept in inner product. So what it is, it's called linear functional and adjoint. Linear functionals we have already learned what is a linear functional, but using that one can define adjoint of an operator. So for example, what is an adjoint? If we have a matrix A, then you can talk about its adjoint. Adjoint means it's just a complex conjugate transpose. So you can tell me quickly, if I give you A, then you can tell me what is it, what it is, what is the complex conjugate transpose of it. You can quickly tell me that. So you know. But you can, as you might have seen by now, that most of the things which you can do for matrices, we can take them to vector spaces also of finite dimension. So by using linear transformation, right? So and whatever we can do for linear transformation, there is a way to go from the space of linear transformation to space of matrices. Now this concept of adjoint is there for matrices, and we want to now introduce this concept for linear operator also, and then we will relate that how this adjoint of an operator is related to adjoint of its matrix representation. Okay, so this is what we are trying to do next. So let me write this first. So we can start from here. It's called the next topic is called linear functionals and adjoint. Functionals I'm saying because the adjoint would be defined by using functional. So linear functionals and adjoint. So before I start before I start this defining this, let me first make this observation. So let us start with by observing something. So at any point, if you have any doubt, you can stop me. Suppose that we have an inner product space V over the field F, let's say, where F is either R or C. Okay, so F is either R or C. Okay. And suppose that we have a vector U in V. Okay. Now, based on this vector U, we can define a linear functional on V. Linear function means it's linear transformation from V to F. So depending on this U, what I can do, I can define this linear functional. Let us call this F subscript U because it is defined by using this vector U. How it is defined? You define this from V to F by the following rule. You take any vector in V and send it to the inner product of V and U for all V in V. Now you can check that using the linearity in the first component of the of an inner product. One can show that this F subscript U, this is a linear transformation from V to F. So that means it's a linear functional on V. So you can check that this F subscript U, this FU is a linear functional on V. This you can verify. This is very easy to verify. All right. So this we can do for any vector U in V. So for any vector U in V, one can define this F subscript U, this linear functional in V. But then the question is, can we do the other way also? That means, so can you tell me what would be the converse of this? What about the converse of this statement? So for every U, there is a linear functional on V of this form, Fu of V is equal to this. Now, let me ask the converse question. Can you tell me what would be the converse of this? So the question is, can we say that the converse is also true? So the question is, how about the converse? So what is the converse here? Can anyone try? So the converse is for a given f in v dash, that means for a given linear functional, does there exist a vector? Let's say that this is just a vector. I'm giving you this notation because I want to say that this is related to f. So u is subscript f in v. So does there exist a vector this such that f of v is equal to inner product of v in f for all v? This is the question. And for this, the answer is yes if v is of finite dimension, and no if v is infinite dimension in the product space. So I'll give you one example. So the answer for this is not in general. That means this is not true for infinite dimensional subspace vector inner product spaces. Not true for infinite dimensional inner product space in general. But yes, if V is of finite dimension. So for finite dimensional product space. So first, let us look at an example of infinite dimensional product space where this is not true. And since for finite dimension in a product space, it is always true, then based on that, we will define adjoint. Okay, so let us look at this example here. So consider V as a space of all polynomials over C, all polynomial functions over C. So what it is, it's a space of all polynomial functions on C. or over C. Okay, and you take this inner product. If you take any two polynomial, then you send it to this one. So this is the inner product, okay, defined on V. So you consider this inner product space. So what we have to do here, we have to show that if there exists. So in order to say that this is false in an infinite dimension vector inner product space, what I need to say? Can you tell me what is sufficient to prove that this question is not true, is or is, it cannot be given, it may not be true or need not be true in infinite dimension inner product space? So what would be enough to show here? Can you tell me? So I want to say that this question is not true, or we cannot answer this for infinite dimension. If I want to say this, what I need to prove or what I need to show?
There exists V such that f of V is not equals to inner product of V with any U.
Yeah, so what I need here, so I need to find the infinite dimension inner product space and a functional on that. At least one functional I need to find on this infinite dimension inner product space such that this is not true. I'm not such that such that for all vectors you have, it's not possible to write it in this way. Right? This is what I'm trying to show. So I've taken this V as a space of all polynomial functions over C with this inner product. Now I first need to find linear functional f, for which I'm trying to say that this f cannot be written in this way. So I'm defining this f by the following law. So let us fix this z. I'm fixing this z. Z is any fixed number in C. Okay, and based on this z, I'm defining. You can take this non-zero also. And based on this z, I'm defining this linear functional on V. Let us call this L from V to C. How it is defined? So if I take V is the space of polynomials. So if I take any polynomial P, then I'll send this P to this PZ. That means it is actually the evaluation of this polynomial at point Z. Evaluation at Z. All right. Now you can verify that. This L is not identically zero. That means it's not a zero functional. It's not a zero functional function. In fact, it is a non-zero functional on V. So that means you can show that it is non-zero, not identically zero, and it is a linear functional on V. That means it belongs to V dash. This also you can easily verify. So can you check that this L is non-zero?
Constant polynomials.
Yeah. Yeah. So this is non-zero and this. Okay. Now the question is, can we find? So if I want to look at this question again, so can I say or can I find a U such that this f of v, which is now L of v here, L of v is equal to v inner product of v comma u for all v. So the question now again, question is, does there exist? So does there exist a polynomial? Let's say RT in V is the space of polynomial such that L of P is equal to inner product of P with R for all polynomial P in V. V is actually this one. Right? This is our V. So this is the question. And the answer, as I said, for this function, you cannot find this. This is what we are trying to do. And how to show that? So if suppose there exists, so the answer is no. Answer is no. Why this is? Because if suppose there exists, suppose that there exists such a polynomial RT in PC such that L of P is equal to inner product of P and R. Suppose that there exists such a R for all P in space of polynomials PC. Okay. Now, by definition, what is the left hand side here? What is L of P?
P
How
of
is
Z.
this function? Yeah, it's a P
P of
of
Z.
Z. Right, P of Z. And what is right hand side? It is the inner product. So it is inner product from integration from 0 to 1 Pt RT bar dt. This is true. And these two things, so these two are equal. So you can say that this is also Pz is equal to this one. And this is true for all polynomial P. Right? So what we have? So we have that Pz is equal to integration 0 from 0 to 1 Pt RT bar dt, and this is true for all P in this one. Right? This is what we get. Now, in particular, if I choose my P, so let's say, so let us set this HT as, so let us consider this polynomial T minus Z. Z is a fixed quantity and T is just a variable. So consider this degree 1 polynomial. Then whatever polynomial I take, so then for every P in this polynomial, if I look at this HP, so what is HPZ? So it's a product of polynomials. That means it's HZ, PZ. What is this? Can you tell me what would be this? H of
Zero.
Z, it's a zero because HZ is zero, H of Z is zero. So for every polynomial P, if I look at this one here, HP of Z, this is zero. Okay. Now look at this, and this is true for all P. So what I can say, so this implies that if I look at this L of HP, then what is the by definition what or by assumption here, since L of P is equal to this, what I can say here, this is equal to this one HPR. So the left hand side here is 0 because by definition left hand side is this one, but this is 0. And what is right hand side? The right hand side is equal to 0 integration 0 to 1 HT PT RT. So H and R, they are fixed, but this is true for all P. Right? So what we can say that this integration here is 0 for all polynomial P. So let me write this. So this implies that this integration is 0 for all polynomial P. Sorry, dt is 0 for all polynomial P in this. Right? So in particular, if I take PT as, let's say, HT bar RT, so this is bar. RT, then what it would be? Then this implies that this is 0 mod of HT square mod of RT square dt. This is 0, right? But then this implies what? What does this imply? If this product is 0, what can we say? This implies that HT, this product is 0. Now, since HT is not equal to 0, because you can see this is a degree 1 polynomial and it is 0, it is 0 only at Z, and it is nowhere it is 0 except T equal to Z, right? So this HT is not 0 except Z. So clearly this RT is 0 at least uh, at the points other than Z. So what you can say from here, that since HT is not identically 0, you can say that RT is identically 0. And you have to tell me the reason why you can say this. So since HT is not identically 0, this H polynomial is not 0, is not a 0 polynomial, then this implies that this R is 0. If this R is 0, I'll come back to this. So if this R is 0, then this is a contradiction, because this, if this R is 0, then here you can see here, this is what we have assumed. If this R is 0, that means L of P is 0 for all P. But if L of P is 0 for all P, that means this L is 0. If this is 0 for all P, that means this L itself is 0. But then we know that L is a non-zero function. So this is a contradiction. So whatever we have assumed that there exists such a R, that is not true. And therefore, we cannot find such a this functional, for this function we cannot find this this R such that L of P is equal to inner product of P comma R. Okay, so this implies that L is identically 0, which is a contradiction. Okay, and therefore whatever we have assumed, that is not true. Now let me come back to this. Why this is true? From here, from the previous line. So this is 0 implies RT is 0. Now I'm saying that since HT is not identically 0, this implies that RT is 0. Now why this is true? So HT is this one, T minus Z. Yeah.
सर RT 0 होगा Z T equal to Z के अलावा सभी पॉइंट्स
T
पर
equal to Z के अलावा सब पे 0 होगा, right?
तो सर कंटिन्यूअस फंक्शन है तो सभी
Yes, yes. Because of the continuity of R, this RT has to be 0 at every point. Okay. So this example answers our question that it is not true, at least in case of infinite dimension inner product space. But in case of finite dimension inner product space, we can always do that. We can always find for a given functional f, we can always find a vector u such that f of v is equal to inner product of v and u for all vectors v in v. Okay. So now suppose that we have, so let me see how much time we have. So now suppose that we have a finite dimensional inner product space. Okay. So now suppose we have a finite dimensional inner product space. And let us suppose f is a, let us suppose f
Hello, sir.
is a linear functional only, right?
Hello, sir.
Yes.
सर L नॉन जीरो होगा तो उसके लिए हमें ये करना पड़ेगा, P को पहले जीरो पॉलिनोमियल नहीं लेना पड़ेगा, और दूसरा ये भी है कि जो Z है वो P का रूट ना हो.
No, listen. L is a function. L is a function from V to C. V is a space of, what
Yes,
is
sir.
V?
Space of
V is a
polynomials.
space of all polynomials. Now, if I'm saying that this function is 0, that means its value is 0 at every point, right?
Yes, sir. Yes, sir.
Now, if I take this Z, this should be true for, so that means P of Z should be 0 for all P. So this function, so see, L is 0 means what? Let me write this here. L is 0 means what? P of Z is 0 for all P,
Yes, sir.
right? But if I take the constant polynomial, does it true? Or is it true?
Yes.
Not true, no? So if I take P as a constant polynomial, non-zero constant polynomial, then P of Z may not be 0. Or right? If it is P is not a 0 polynomial, then and it's a constant polynomial, then it is not 0.
हमें
So there
ऊपर
are
लेके तो नहीं चलना पड़ेगा पी को जब नॉन जीरो ले चल रहे हैं मतलब बोलना पड़ेगा ना
no P से मतलब ही नहीं है मुझे. This is what I'm saying is that if L is 0, suppose that if L is 0, then by
Yes, sir.
definition P of Z is 0 for all P. Now if suppose Z is 0, suppose that Z is, if I, so this Z is a fixed number in C. So if Z is 0 and if I take P my constant polynomial, let's say 1. So can I say that P of Z is just 1? So 1 is equal to 0. This is not true. Now if suppose Z is an
जीरो
क्या क्या
पी जीरो
so if P is 0, if P is 0, then that is a particular polynomial. But I'm saying that if L is 0, then that implies P of Z is 0. This should be true for all P, and you are checking for a particular P. Is it okay now? Did you realize your mistake? Is it okay now? Okay. All right. So let us discuss the finite dimension case. Suppose that V is of finite dimensional and L is and let F be a functional on V. Okay. Now we want to find a vector U. So what we are trying to do, we are trying to find. So we are trying to find U in V such that F of V is equal to inner product of V comma U for all V in V. This is what we are trying to do, right? So keep in mind that this is what we are trying to do. We are trying to find a U, such U, so that we can write F in this way. And what we are given a finite dimensional inner product space and functional on V, linear functional on V. All right. So let us suppose, since we are in finite dimensional inner product space, we can find a basis for this first. So let us fix an orthonormal basis. So let Q1 to Qn. This is an orthonormal basis of V. Now if I take any vector in V, then I know how to write this vector V in terms of this basis vectors. Can you tell me what would be V if I want to write this V in terms of this basis vector Q1 to Qn? What would be this vector V?
Summation of
Summation I equals to 1 to n inner product of V with Qi into Qi.
Right. So this is, now if I take f of V, then what would be this? So this would be f of this summation I equal to 1 to n V Qi. Now can I take this f inside
yes,
summation
sir.
inside because of linearity? So I can write this I equal to 1 to n V Qi, the inner product of V with Qi. This is just a scalar, right? So it would be f of qi. Now this f, this is a scalar here, and f is a linear functional. So f of qi, this is also a scalar. So I'll write f qi first here. Okay, so I'll just rewrite this thing. So I'll write it as f qi, same thing, v comma qi, because both are scalar, so I can write it in this. Now I want to take this f of qi here, this term inside this inner product, because I want to produce a vector u. Keep in mind that this is what we are trying to do. We are trying to produce a u such that f of v is equal to this for all v. So I'm trying to do that. Now, can I take this inside? If I want to do that, then what it would be? So basically what I'm saying is that I can take this, I can write this as fqi bar qi. Sorry. Right? And then since this summation is over indices index I, so we can take this summation also inside. So it would be, you can check that this is just because this follows because of the inner product and linearity of v. So this would be v summation I equal to 1 to n f of qi bar qi. Now you can check that whatever vector I have produced here, I can call this as u. I can call this vector as, let's say, uh, this vector as u. Let's say. So let me write this again. So this vector I can call as u, and you can see that this vector doesn't depend on v. It only depends on the linear functional f and the basis vectors which are fixed. So you can say from here that if I call this vector as u, then I can write this, I can write as f of v, we can write as v. So, or maybe I can write, I can call this as u subscript f, just to say that it depends on f. So this is just u subscript f. So we can write this v f as this way. So this answers our question for finite dimension intervals. Yes.
सर यहाँ से ये भी कह सकते हैं ना, ये u यूनिक होगा.
Yes, this u would be unique. So I was coming to this. So in fact, one can say that you cannot find such a u, another such a u, or you can see that, or you can say in other words that this u subscript f, whatever vector we have found here, that is a unique vector in V, such that f is written in this way. Or what I'm saying is the following, that you can also say something about the uniqueness. So how to show that it is unique? So suppose that suppose there exist UF and WF, two vectors in V, such that f of V is equal to inner product of V comma UF, and this is also equal to inner product of V comma WF. This is true for all V. Suppose that this is true. Now what does it mean? It means that V U of f equal to V W of f for all V in V. Now why from here we can say that WF is equal to U of f, UF. So what we can say from here, we can say, if I take this to other side, I can say V minus UF V comma UF minus WF equal to 0. This is true for all V. Now can you say from here that UF is equal to WF?
Yes, UF minus WF must be 0.
Why?
सर v तो
क्योंकि
कुछ
V equal to
equal
UF
V
minus WF.
0 होगा.
For
Yeah,
all
so
V.
yes, so here this is true for all V. So in particular, if I take V as UF minus WF, then what it would be? It would be UF minus WF, comma UF minus WF equal to 0. But what is this side? This is the inner product of a vector with itself. This is 0 if and only if, because of the inner product property, UF minus WF is 0. But this implies that UF is equal to WF. So this is also whatever vector we have found, that is also unique. Okay. So now you can see that this way, so we have seen that if we have fixed a vector in U, then depending on this vector U, we can define a linear functional on the vector space. And if on the other side, uh, if we start with a linear functional or an element in V dash, then we can find a, there is a way to find a unique element in V. So this, using this, we can define an isomorphism, in fact, from V to V dash. We'll see that, but this is what you can say from here. So conclusion is that if V is a finite dimensional inner product space and F is a, so from this observation, what we can say that, so let me write the conclusion from whatever I did here. Uh, so the conclusion is the following, that if V is finite dimensional inner product space and F is a linear functional on V, then there exists a unique vector, let's say U F in V, such that F of V is equal to inner product of V and U, all V in V. This is what we have proved. Okay. Now with this preparation, I can define adjoint of a linear operator on an inner product space. All right. So let us define that. So I am defining first what is an adjoint of a linear operator, and then we will see whether whether adjoint of a operator exists or not. Okay. So let us first define this. So what I'm going to define is adjoint of a linear operator, on an inner product space. Okay. So let us define this. So let V be an inner product space. So I'm giving you the definition first and then we'll discuss. So suppose that we have an inner product space V and T be a linear operator on V. That means it's a linear transformation from V to V. Then this T has, then we say that this T has an adjoint. T has an adjoint on V if there exists a linear operator S on V such that this expression is true, or this expression holds. So if you take the inner product of T of U and V, this is equal to inner product of U and S of V. This is true for all vectors UV in V. Okay. So this is the definition of an adjoint, that if we have an inner product space V and a linear operator T, then this T has an adjoint on V if there exists a linear operator S in on V such that this expression is true. then we say that T has an adjoint, and this S is called adjoint of T. Okay, so this S, this linear operator S is called adjoint. So N S is called an adjoint of T. We'll see whether adjoint is unique or not in the next. So this is the definition, and we are not talking about existence of an adjoint at this point. But what I'm saying next is that we don't know whether adjoint of a linear operator exists or not. But if it exists, it is unique. There cannot be two adjoint of a linear operator. So if T has an adjoint on V, then it is unique. That is what I'm trying to say here. So you can say that if, so this is the definition I gave. Now, based on this definition, I'm saying further that if T has an adjoint on V, then it is unique. I don't know whether adjoint will exist or not, but if it exists, there cannot be two. So how to prove this? So suppose that so proof, here we can prove this. So suppose that T has two adjoints, let's say S1 and S2. So let S1 and S2 be two adjoints of T. Okay. So what does it mean? By definition, this implies that Tu of V, inner product of Tu and V, is equal to inner product U S1V, and this is also equal to, because S2 is also in an adjoint, so it is also equal to this one. And this is true for all U V in the vector space V. Okay, so what we can say from here, that U S1 of V minus S2 of V is equal to 0 for all UV in V. Okay, now from here, what we are trying to show, we are trying to show that S1 is equal to S2. This is what we are trying to show, right? Now what we can say from here, so this expression, whatever I have written here, this is true for all U and V, for all vectors UV in V, in the vector space V. So what we can say from here, so from here, you see here, if I fix a V, so this expression is true for all UV. So for a fixed V, I can say that this is true for all S1V minus S2V is 0 for all U in V, right? If I fix V and if I vary U, then this is true. But then, as we gave similar reasoning previously, using the same reasoning, we can say that this implies that S1V is equal to S2V. But then I have fixed a V, but this is true for all V. So you can say that this is true for all V in V. But then this implies that S1 is equal to S2. So if T has an adjoint on V, then it is unique. Since it is unique, we can fix a notation for T. So since the adjoint of T is unique, we can denote it by fixing a notation. So since adjoint of T is unique, we use the notation T star for this. We use the notation T star to denote the adjoint of T. Okay. Okay. So what you can see here, can you tell me the on what things adjoint of an operator depends on. So you just look at the definition of adjoint. What things adjoint of an operator depends on. It depends on the operator itself. Not only on the operator, it also depends on the inner product. You can see here how it is defined. So this S, of course, if you look at this expression, this S depends on T, and not only that, it also depends on the inner product. So if I change the operator, then I will get a different adjoint. Or if I change for the same operator, if I change the inner product, then also the adjoint changes. So adjoint of a operator not only depends on T but also on the inner products. So this is also an important point here to mention, that T star depends not only on T but also on the inner product. Okay. Now this is the uniqueness, but what can we say about the existence of an adjoint? So as I mentioned, as we have already seen, that we answer something for finite dimension, but the similar thing is not true for infinite dimension. Because of that reasoning, one can say that if T is a linear operator on an infinite dimension in a Proteus space, then this operator T may or may not have an adjoint. But if T is a linear operator on a finite dimension inner product, then it will always have the adjoint. Okay, so existence of operator is certain on a finite dimension inner product space, but it is not true in general for an infinite dimension inner product space. We need further conditions on the infinite dimension inner product space. And this thing will be clear when we prove the finite dimension case. So actually, in the finite, while proving the existence for a finite dimension inner product space, existence of an adjoint of an operator on a finite dimension inner product space, in the proof you will realize that since a similar thing is not true for infinite dimension, therefore the proof will not work for infinite dimension. So whatever observation we made here,
Hello,
so
sir.
here you look at this conclusion here. This will be useful for us to prove the existence of adjoint on a finite dimension network space. Yes.
तो जो आपने
You want
ऑब्जर्वेशन दी है, तो जो आपने ऑब्जर्वेशन दी है और आपने जो डेफिनेशन दी है, तो इसको सर कैसे लिंक किया वो समझ में नहीं आया। तो कैसे
कौन
लिंक
सी
किया मतलब समझ नहीं आया।
कौन सी
तो
डेफिनेशन?
डेफिनेशन है एडजॉइंट ऑपरेटर की।
No, definition is not linked. No, definition is not linked to whatever we had observed. So it's just the way we define here. It's just a definition. Now, in order to prove the existence of an adjoint, this observation will be useful. That's what I'm saying. This definition is not. We can define this adjoint first, and then we can make the observation. Absolutely fine. But this observation I will need to say that every operator every linear operator on a finite dimension inner product space has its adjoint. But the same thing is not true for infinite dimension inner product space, because we have also observed similar thing for infinite dimension, that this kind of thing is not true when V is infinite dimension. So the answer to your question is that this definition doesn't depend on the observation we made. But now the next thing, that means the proof of the existence of the adjoint of a linear operator on a finite dimension product space, that will use heavily whatever we have observed here. Okay.
Yes, sir. Yes, sir.
Okay. So maybe I'll just write this result, but in the next class we will prove. So as I mentioned that in the proof we will use the observation we made that for every linear function, or there is a natural isomorphism from an inner product space to its dual space, as this is what we have observed. So one can define an isomorphism from V to V dash using that observation, and that isomorphism will be useful in order to define this adjoint. So I'll just state this result, and in the next class we'll prove this, and then we'll still be we'll still left with 2-3 minutes. So if you have any doubt, you can ask. So let me state this result, and then we will stop. So this is the existence uh, of adjoint on a finite dimension inner product space. So let V be a finite dimension inner product space and T be a linear operator on V. Then T has an adjoint on V. That is, what does it mean? That means there exists a unique operator T star. This is the notation we are using for adjoint T star on V, such that inner product of T of U comma V is equal to inner product of U comma T star of V for all UV in. This is what we will prove in the next class. So if you have any doubt, you can ask. We still have 2 minutes.
So, can
Yeah.
adjoint be defined on linear transformation?
So we are defining this for linear transformation only. So here we are defining we are talking about linear transformation adjoint of a linear transformation. So operator is a linear transformation. So it is so you are saying that for general transformation, this is what
Yes,
you
sir.
are saying.
Yes, sir.
So that means a linear transformation from V to W.
Yes, sir.
So basically that is like you need to see how you want to if you look at how these things are defined. So you are using inner product. So basically you need a sort of same inner product on the codomain also, right? Because T of you are taking the inner product of an element in domain and in the codomain, right? Here, if you look at
Yes, sir.
here, so basically you need the same inner product. Not only same inner product, you need same space also. Then only it is true. So basically you need the same inner product space. So it has to be an operator.
Yes, sir.
Okay.
So, आपने जो
Yeah.
QR डिकम्पोजिशन करवाया था उसके रिलेटेड मैंने एक आपको मेल करा था, तो क्या आपने
हाँ,
उसको
वो
रीड
मुझे
आउट
समझ नहीं आया आपसे, मतलब what are you interested in actually? I did not get what you were asking.
सर? आई एम आस्किंग दैट कि जो आपने क्यूआर डिकम्पोजिशन करवाया था वहाँ पे आपने बताया था कि वो आइगन वैल्यू की मतलब अप्रोक्सीमेट आइगन वैल्यू देता है क्यूआर डिकम्पोजिशन.
No, not approximate eigenvalue data hai. So QR decomposition doesn't give you eigenvalue. It is a tool that is useful in eigenvalue algorithms in the computation of eigenvalues. So eigenvalues are computed by using QR algorithm. So I'll come to these points when we start QR this eigenvalue eigenvectors, but we have not started these things here. But since you have asked, and I also mentioned in my previous lecture that this QR decomposition is very useful. It has a lot of application, and one of the it has a lot of application means it can be used in solving a system of equation. It is also useful in solving this in finding eigenvalue eigenvectors. So for finding eigenvalue eigenvectors, QR algorithm is used, and in QR algorithm, this QR decomposition is used. So basically, QR decomposition gives us a tool to solve this eigenvalue computation problem approximately. So it itself doesn't give you eigenvalue of a matrix. So it doesn't mean that. So if you have a matrix A and if I give you its QR decomposition, you won't be able to say anything about eigenvalue eigenvectors. You need to do further a few things in order to say something about the eigenvalue eigenvector. So that means basically for this A, you need to transform this A into a simpler form. If you remember in my lecture, I said that what is this QR algorithm? The basic idea of this QR algorithm is that if you are given a square matrix A, then it converts or it transforms this matrix A into an upper triangular matrix. Because for upper triangular matrix, finding eigenvalues is very easy because it's just the eigenvalues on the diagonal entry. So what this QR algorithm does, it transforms A in an eigenvalue preserving way. That means you transform this A under some similarity transformation to some other matrix U, such that this A and U have the same eigenvalues. And this in this transformation, this QR decomposition is used. Okay.
यस सर, मैं भी यही कहना चाह रहा था कि मतलब वो अप्रोक्सीमेट अप उसकी हेल्प से अपन आइगन वैल्यूज फाइंड कर सकते हैं अल्टीमेटली।
यस।
और सर हमने अभी रिसेंटली ही ओडी में सिस्टम ऑफ ओडी पढ़ रहे हैं, तो वहां पे सिस्टम ऑफ ओडी अगर इन पर्टिकुलर अपन कांस्टेंट मैट्रिक्स लेते हैं तो वहां पे आइगन हायर ऑर्डर में आइगन वैल्यू फाइंड करना डिफिकल्ट हो जाएगा, तो वहां पे इसका यूज करके सिस्टम का सॉल्यूशन अप्रोक्सीमेट फाइंड किया जा सकता है।
Yeah, so not only for this, whenever there is a matrix and you need to find eigenvalue, whether you are solving system of equation or you are doing some other thing with the matrices. If you need eigenvalue eigenvectors, there is no way to compute eigenvalue eigenvectors exactly for a generic matrix, for a general matrix. You need to compute them approximately. So you need this algorithm. So no matter whether you are solving a system of differential equation or some other thing, if you need eigenvalue eigenvectors, you need to use this algorithm, or you need to just approximate.
ये सब बट जो आपने अभी जस्ट बोला कि यहाँ पे कुछ और भी चीजें लगेगी जो यूज होगी अप्रोक्सीमेट करने के लिए, तो
yes.
वो तो मतलब या तो हमें आप
so your question is no, so I understand now. So you want to understand what is this QR algorithm? This is what you are saying?
Yes, sir.
So you want to learn. So I can, that is. So you just say that, sir, I want to know how to understand, how to compute this eigenvalue eigenvector. So I can give you a reference. Okay, I can give you a reference for this. You just read it, and if you have doubts, you can discuss with me. The thing is that it's not like you will directly understand this algorithm, because how to transform this A into an upper triangular matrix needs a lot of things. So the basic idea is that you transform this A into an upper triangular matrix, but to do this practically, I mean to do this in a practical way needs some other tools also, some other things, how to convert A into an upper triangular in such a way that the eigenvalues are preserved. That may need some other like reading also. So I'll give you a reference of a book, and I will also mention chapters which you might need to read in order to understand that algorithm. Is it okay?
Okay, sir. Thank you.
Yeah. Okay, so it's time we can stop now, and I'll upload this lecture. So the quiz would be on Saturday at 11 a.m. Thank you.
Thank you, sir.